All right, so as Therese said, I will be speaking about the number of n-queens configurations. And if any of those in the audience were actually present at the members seminar at CMSA about 1 year ago, I spoke about the same problem. But then I didn't know that I was actually going to solve it within a year. So this will be a different talk. Okay, so I'll start by telling you what an n-queens configuration is. And the story begins with a well-known chess puzzle. So a chessboard is an 8x8 grid, and one of the pieces in the game of chess is called a queen. And queens can attack laterally across rows and up and down across columns, and also diagonally in either direction. And there's this puzzle. Can you put 8 queens on a chessboard so that no two are threatening each other? So no two are allowed to share a row, column, or diagonal. And 8 is definitely the maximum, because the chessboard is 8x8. You can have at most 1 queen in each row. So you definitely can't put more than 8 queens on the board. But in fact, you can put 8 queens on the board. And I invite you to try to solve this yourself. It probably won't take long. Or you can just look at these solutions on the slide. But of course, as mathematicians, we immediately ask, well, is there anything special about the number 8? And the answer is there isn't really. We more generally can ask about the n-queens problem. Take an n by n board, maybe n is a million or a billion or 13, as is the case here. And now try to put n queens on it so that no two share a row, column, or diagonal. And then the first question would be, is this possible? And the answer is not very difficult. The answer is always yes, as long as n is at least 4, you can find such a configuration. And here is an example for n equals 13. And then as I'm a combinatorialist, so the next step after you ask, does an object exist, is you want to count these objects. And this is what's become known as the n-queens problem, which is basically what can we say about Q of n, which is the number of n-queens configurations. And yes.
Why you need 4? Did I heard you correctly? You said you need 4.
Oh, I did say that you need n to be at least 4. So it's just kind of, I guess, the 2x2 boards and the 3x3 boards, you can just kind of check that you won't be able to find such a configuration. So but 2x2, it's easy, because the only way to place 2 queens so that they don't share rows or columns is if they're in the same diagonal. And for 3x3, you just perform a similar check.
Right. Sorry, I just thanks for the confirmation.
Yeah, but I should say, please just interrupt me. You don't even have to politely raise your hand, like Therese just did. Just please interrupt me and unmute yourself if there are any questions. I'd rather talk about what you want to hear than just go on and on talking to myself. Anyway, this is the question that I'd like to address today. What can we say about Q of n, which is the number of solutions to the n-queens puzzle? So this problem, as you might imagine, has been fairly well known for a while, so it has some history. Before I get to the ancient history, I'll just say like the easy things to say are regarding upper bounds. So not much was known. Every n-queens configuration is in particular a permutation matrix, because you have 1 queen in each row and in each column, and the number of permutations is n factorial. So Q of n is definitely less than n factorial. This is a very easy bound. And n factorial, I'm writing it this way, n divided by e to the power of n times some error term, which you can safely ignore, because this is the form that most of the other bounds in today's talk will take. And in general, I haven't said the main result yet, but in general, like improving these error terms would probably, in any of these things, would lead to new breakthroughs. So I'm not going to say much more about them. Just they're there, and we don't know what to do with them. Improving them would be amazing. There is one other upper bound on the problem from a few years ago, which is that Q of n is at most, well, this, n divided by e to the power of something bigger than 1 to the power of n. And I'll say a little bit about this one. It uses something called the entropy method, which will play a role in my own proof. So I'll say a little bit about this one later. Now, in terms of lower bounds, so famously to me, Gauss himself thought about this problem, and he found 72 solutions for the 8 queens problem. In fact, there are 92, and there's like some probably incorrect story that Gauss claimed that 72 was all the solutions, but it's more likely that he just didn't think about it for more than an hour, and that's all he found. Then in 1874, kind of the n queens problem, as I posed it, became known, and it was shown that for all n that there are at least 4, there is at least one solution, and there are some improvements. For example, this one from 94, which is an exponential lower bound on Q of n. But though I haven't written it in the slide, this bound and also this super exponential bound from 2017, they actually don't hold for all values of n. They require n to satisfy some arithmetic condition. So basically, until just a few months ago, there were no lower bounds on Q of n that were bigger than like 17 that held for all values of n. And then the result that I'd like to kind of talk about today is my own result from just a few months ago. It says that there is a constant, which I'm going to call beta, and I've pinned it down to some degree of accuracy, approximately 1.94, such that the number of n queens configurations is n divided by e to the power of beta to the power of n. So I'll say now, I mean, you'll see like later in the talk exactly how this is the case, but this constant is the solution to a convex optimization problem, which probably doesn't have a nice closed form, which is why probably the best one can hope for in terms of explicit bounds are kind of solving the optimization problem to whatever degree of accuracy you want and going with that. Okay, so this is what I want to talk about today.
Question?
Yes.
What does this plus minus mean? Is that a lower and upper bound or?
Yeah. Okay. So there are 2 plus minuses here. There's beta equals 1.942 plus minus this thing. So by this I just mean that beta is contained in the interval 1.942 plus whatever it says here, and minus whatever it says here. And over here I mean something similar, except that this little o of one term, what I mean is that it's something that depends on n but tends to 0 as n tends to infinity. And whatever is written in these parentheses, it could be a little bigger than 1 or a little smaller than 1. But the point is that it tends to 1 as n tends to infinity. I think that you could, whenever you see a plus minus in the rest of the talk, you can probably just ignore it because it probably just means some error term that I'm writing for correctness, but is not actually a big part of the story. Okay. But yeah, thank you for that question, and please keep them coming. Okay, so I'd like to kind of put a more modern perspective on this problem. I mean, so far I've just told you like about a puzzle and something about bounds on this puzzle. But it turns out that like this puzzle kind of fits in very nicely with a lot of things that have been happening in combinatorics in the last 10 or even maybe 20 years, but not much more than that. So there's a field of combinatorics called combinatorial design theory. And kind of abstractly, it deals with what we would call hypergraphs with some regularity. And here are some examples. So regular graphs. A graph is a collection of vertices and edges. A graph is regular if every vertex is in exactly the same number of edges. So this is an example of a combinatorial design. Here's another one. A Latin square. It's usually defined this way on like this matrix on the bottom right, but one equivalent way of thinking of it is as in this case, a 3 by 3 by 3 matrix, more generally n by n by n. And if you look at this matrix, you'll see that in every line, whether it's a row or a column or a shaft, and in any layer, there's exactly one black space and all the rest of the places are white. So this is kind of a higher dimensional version of a regular graph. Every line contains exactly one black thing. A Steiner triple system, which is an example of what are called more generally Steiner systems. So this is, well, here I have 7 vertices, and I've divided them into triples of vertices with the property that every pair of vertices is contained in exactly one triple. So this is, again, some kind of regular hypergraph. More generally, we have this definition of NQR Steiner systems. And I don't want to get into this too much, but I do want to say that even the existence of NQR Steiner systems for more than a very small number of values of Q and R was not known until about 7, well, maybe 8 years ago. And kind of the methods that were used to prove the existence of these systems have become since then very influential, and they do make an appearance in the result that I'll talk about today. And this is due to Peter Kivash of the University of Oxford, this existence theorem. Okay, so here are just some recent breakthroughs regarding combinatorial designs. So the entropy method, which I've already mentioned, and I'll talk about again, you use this to upper bound the number of combinatorial designs. Randomized algebraic instructions, this was originally used to prove the existence of designs. Then subsequently, there was an alternative proof using a different method called iterative absorption. But all of these methods were used to kind of attack problems initially that were very, very symmetric, such as the ones that I showed you, regular graphs, Latin squares, Steiner triple systems. And the n-queens problem does kind of fit into the story of combinatorial designs because you have a regular structure. Every row and column has exactly one queen, but it is far less symmetric. The diagonals are different lengths, and this kind of makes the problem more difficult to analyze. It's not clear how to apply any of these methods directly. And I'll show you why in more detail later. So anyway, this is kind of like the modern perspective of the last few years. And because of this asymmetry, actually for many years, people, like most mathematicians, wouldn't even think about the n-queens problem itself. They would think about something called the toroidal n-queens problem. And this one is much more symmetric. What you have is the same setup where you have an n by n chessboard and you want to put a queen in each row and a queen in each column that do not kind of share diagonals. But here you let the diagonals wrap around the board. So if you get to the top, you go down to the bottom. And this makes everything more symmetric. All the diagonals now have the same length. And you can kind of, if you cycle the board right or up or down or even rotate it, you get the same problem. So this would seem to be easier to solve. And then you can say, okay, well, instead of Q of n, let's define T of n, which counts the number of toroidal configurations. And definitely T of n is less than Q of n because every toroidal configuration is in particular a classical configuration. So maybe, the best we can do to understand Q of n is just to understand T of n, at least in terms of lower bounds. And kind of one theorem from a few years ago is an upper bound on T of n. It's at most n over e to the 3 to the power of n. And had I given this talk 1 week ago, this would have been a conjecture. But yesterday I had to update my slides and say that actually this is now a theorem that this upper bound of T of n is tight. So in fact, T of n is equal to this term over here. And this is a spectacular result due to Candy Bautel and Peter Kivash that was posted just last Friday. If you'd like to hear more about this result, then I encourage you to scan this QR code and sign up for the Combinatorics, Physics, and Probability seminar. I apologize for the plug. Later this semester, Candy Bautel will be speaking about this. And Peter Kivash will also be speaking in our colloquium on November 10th, but I don't know if it will be about this or something else. So this is a spectacular breakthrough. The proof is 160 pages long, so I imagine it'll take a while for the community to kind of digest it. But it was also quite unexpected. Anyway, so I'd like to kind of go back to the original talk dealing with the n queens problem. And one of the methods that I've already mentioned is the entropy method, which is a very nice and simple method that you can use to prove upper bounds on the number of objects with some regularity. And what you need to know is the following. So many in the audience probably have some background with entropy methods, and this will be completely obvious or just known. But I do want to make sure that everybody can follow, because I'm actually going to do a proof. So suppose we have a random variable x, which takes values in a finite set. Its entropy is defined according to some formula. And intuitively, you could describe this as the amount of information that you need to communicate an instance of x on average. What you need to know about this function is the following. The entropy of x is at most the logarithm of the number of values that it can take, and equality holds if and only if x is distributed uniformly. There's also something called conditional entropy. So if you have a pair of random variables, take values in a product space, s times t, so you can define the conditional entropy of x given y. So intuitively, you would say this is the amount of information that I need to kind of communicate an instance of x to you, the audience, if you already know the value that y took in this experiment. And this is, well, it's defined according to this formula as follows. It's the expected entropy of x, where the expectation is taken over the distribution of y. It's something. And then you have a chain rule, which is a fact that you would need to prove, which is that if you think of xy as its own random variable, then it has its own entropy. And in fact, this entropy is equal to the entropy of y plus the conditional entropy of x conditioned on y. All right, and yeah, and now we will be doing a proof. So hopefully now you all see a writing pad, and you should see this theorem of Luria's from 2017. So this is not a result of mine in any way, but it is a very nice introduction to the entropy method, and it gives a flavor of one of the main ingredients that are used in my own proof. So before I start, if there are any questions, now would be a good time. All right. So here's what we're going to do. We want to prove that the number of toroidal configurations is at most n over e to the third to the power of n. So what we do is let x be a uniformly random toroidal n queens configuration. So if you recall from the entropy method, you know that the entropy of x is equal to the logarithm of the number of values that it might take, which, since it's distributed uniformly among the set of toroidal n queens configurations, is just going to be the log of t of n. So if I can prove any bound on h of x, I'm proving a bound on t of n as well. And now what I do is I say, okay, so let x1 to xn be a uniformly random ordering of the queens in x. So, I mean, x is a queens configuration, so it's just a set of n queens that are located somewhere on the board. So I can say, okay, I take these queens, I draw x at random, and now I do another random experiment. I take these queens and I just order them uniformly at random from x1 to xn. So now I have, new random variables, x1 to xn, and I can ask what their entropy is. Okay, so using the chain rule that I mentioned before, you would say, well, actually knowing x1 to xn tells me what x is. It also gives me a little bit of extra information, which is the extra information pertains to the particular ordering at which I'm looking at these things. And if you kind of do the arithmetic, you see that the entropy of this sequence is equal to the entropy of x plus the entropy of the random ordering, which would be log of n factorial. So this uses the chain rule. But now I can once again use the chain rule inductively and say, well, consider the following process. Instead of looking at x all at once, suppose that I reveal the queens from x1 to xn sequentially. So at the start of the process, I don't know anything about the configuration, and then I'm told what x1 is, and then what x2 is, and then what x3 is, and I can look at this process and ask how much information is needed at each step to specify the next queen. So this is an inductive application of the entropy rule. So this would be the entropy of this thing would be the same as summing from 1 to n of the conditional entropy of xt given all of the previous queens. All right, so now I'm in the situation where in order to bound h of x, what I want to do is find bounds on supposing that I know t minus 1 queens out of a configuration. How much information do I now need in order to find out what the next queen is in a configuration? So now I can start actually drawing, doing combinatorics and drawing queens configurations. So the situation is this. Here's my chessboard. Okay, that did not come out the way I wanted. Let's try again. That's better. And now what's happened is I've revealed a few queens because I'm somewhere in the middle of the process. So by revealing these queens, now I know that there are positions on the board that I can no longer use. So anything that shares, that row or that column, or this toroidal diagonal is out of the question, and also this one, and also for the other, two queens that have been revealed, I've now blocked off a bunch of places on the board. I think that's it. And whatever the next queen is going to be, given that I already know these three queens, I know it's going to be somewhere in the available positions. So these would be the positions on the board that do not already share a row, column, or diagonal with a queen. So xt will be an element of a of t, a for available instead of available positions. This means that xt is a random variable, takes values in this set at. So if you remember what I said about entropy before, this means that h of x of t is less than or equal to the logarithm of a of t. The entropy of a random variable is always less than the log of the size of the set in which it takes its value. Now, actually, a of t is a random set. So it's not quite the situation I had before. You really need to put an expectation here. Okay. Now I'm going to say, well, the logarithm is a concave function. So the expectation of the logarithm is always less than the logarithm of the expectation. So now what I have to do, my task now, is to try to understand this expectation of a of t. And here's where the symmetry of the toroidal problem comes into play. What is the expectation of a of t? Well, there are n squared places on the board. And because we're in the toroidal setting where all the diagonals have the same length, these places are indistinguishable from each other at the start of the process. So whatever the expectation of the number of available positions is going to be, it's going to be n squared times something. It's just going to be n squared times the probability that after t steps of the process, a particular position in the board is available. So it's going to be n squared times something. Now, what is this something? So say I fix my position at the start of the process, and I want to know after t steps of the process, what is the probability that it will still be available? Well, this guy over here shares a column with a queen. He shares a row with a queen, and also, the diagonals are shared with the queens. And there are 4 queens that could make this guy unavailable. What I need to know is that, well, this guy will be available if and only if none of these 4 queens were revealed in the first t steps of the process. And because the ordering of the queens was random, the probabilities that these 4 queens will have been revealed are essentially independent. So I'm going to get something to the power of 4 for the 4 queens. And the something is going to be 1 minus t over n. So you can check that 1 minus t over n is basically the probability that a specific queen will have been revealed in the first few steps of the process. All right, so now what I do is I take this thing, I plug it into this sum, so I get, h of this thing is less than or equal to the sum of, well, of this thing, which is less than, this thing, log of n squared 1 minus t over n to the fourth. And if I take, you can calculate this sum fairly precisely. If you then take it and plug it into this formula over here, then you get the desired bound on h of x, which gives you this upper bound on t of n. All right, so that's called the entropy method. And it's a beautiful method. It hasn't been known for very long, but it's fairly simple. You don't need to know a lot in order to apply it. And it's been very powerful in getting upper bounds on these combinatorial designs kind of things, like this toroidal problem. Okay, now would be another good time for questions, if there are any. Okay. So moving on, of course, I've been talking about the toroidal problem. And I already said that I proved an upper bound. The corresponding lower bound is known now, but of course hasn't been known for a long time. And the only thing that I've changed in this slide since this breakthrough is the fact that it's now says theorem here and not conjecture. But here is an almost proof of this theorem. And in fact, this is how the real proof went, except I'm leaving out about 160 pages of important details. So here's how you generally prove lower bounds in the numbers of combinatorial designs. So the paradigm is called random greedy plus absorption. And it goes like this. You run an RGA, a random greedy algorithm for, in our case, the toroidal Queen's problem. So what this means is you start with an empty board and you choose a place uniformly at random and you put a queen on it. This blocks out, makes unavailable some of the positions in the board. But now you look at the remaining positions and you choose one of them uniformly at random and put a queen on it. This blocks out more positions. You look at the remaining ones, put a queen on it, and so on and so forth. It turns out that this algorithm, with very high probability, so you can't say for sure because it's a random algorithm, but with probability very, very close to 1, will actually succeed in placing almost n queens on the board, but not quite n. You will get stuck somewhere near the end. But furthermore, it not only succeeds in placing so many queens on the board, you can also control how, you can track how many available positions there are at each stage. So you can know how many choices the algorithm could make. And this gives you a lower bound for the number of ways that the algorithm could run, right? And here's the lower bound. It's, some formula. And now the next step is, okay, so I take the outcome, the output of this random greedy algorithm, which is an approximate n queens configuration. And now just complete it. Okay, so stop doing things at random, do something smart and clever to place a few more queens on the board so that you get a complete configuration. And this would give you a lower bound of n over e to the third to the power of n. Now, the reason why this is an almost proof, of course, is, well, I've left out a lot of details, but the crucial details turn out to be how to complete this thing. So again, until 1 week ago, I would have said this is like nobody has any idea how to do this. Now, it seems to be the case that it is known to some people how to do this, not yet to me. But kind of one important observation for the classical case, which makes it significantly easier in this regard than the toroidal case, is that so it actually is easy to complete the output of this random greedy algorithm to a classical solution where the diagonals don't wrap around the board. So you run the random greedy algorithm as if you're doing it for the toroidal case. And this is fairly easy to analyze with existing tools. But then once you get stuck at the end, you no longer work on the torus. Now you just work on the classical problem, and you can complete this to an exact solution. I'll show you how in a moment. But this gives this upper bound up here, n over e to the third to the power of n, on the number of solutions to the classical problem. So this is due to myself and Luria. this is a paper that was posted last May. Kind of the Bautel and Kivesh's work on the toroidal problem also just gives an independent proof of the same thing using their own methods. So
Can I ask a question?
yes, of course.
It's a question about the random greedy algorithm.
Mm-hmm.
So just wondering, like, if you can estimate at what point do you make a mistake, right? So if you start randomly, initially, I mean, almost certainly this is a legitimate configuration, right? But
Yeah.
at some point you'll make a mistake, right? And this, and I mean, does that
Well, so the way
worthwhile
I mean,
to
okay, so
estimate?
I think the way you actually set it up, hopefully this will answer your question, is that you cannot make mistakes, because what you do is that you run the algorithm step after step, and at each step you look at the queens you've already placed on the board, and you look at the positions that are still available, and you choose the next queen at random from those positions. So you're definitely not going to conflict with the previous choice. Well, what could happen is that you'll get stuck. You could say,
that's what I mean. But at some point, you necessarily get stuck, right? Or is this?
okay,
So,
yeah,
so there is kind of threshold at some point that you cross, right? Or am I misunderstanding it?
No. This is an excellent question. So probably you get stuck. You probably are not able to run this algorithm all the way to the end. The point where you get stuck in is very close to the end. So you will have definitely succeeded in placing 99.999% of the queens on the board before you get stuck. I say definitely, it's actually not definite. It's just with extremely high probability. But you probably won't succeed in placing 100% of the queens on the board. And then there's a question of how many queens are missing. I do not know the answer. I don't think this answer is known. These kinds of questions tend to be difficult, but they certainly are studied in some contexts. I mean, I could hazard like a reckless guess, but maybe I shouldn't. Okay. Does that satisfy you as an answer?
Well, I didn't think you would have some kind of answer out of the pocket, but yeah, I guess I was asking also, even if the last queen you place where you get stuck, you could have been like, without knowing it, stuck a little bit before, right? Because just the configuration that you got was not containing any fully legal configuration that solves the problem. So I was just wondering conceptually whether there is like a kind of horizon that you cross and then.
I mean, these are good questions. So I mean, like the way that you actually do these, and difficult questions, like, so what happens with these processes is that you kind of what's called maintain control of them, which just means we understand what they're doing until a certain point. And kind of fortuitously, this point is very near the end of the process, but there is some point at which like we just don't know how to analyze them, whether it's because the methods that we have are not developed enough, or just because actually the process is no longer concentrated like along any particular trajectory. So what you actually do when you're writing these proofs is you say, okay, I'm not actually going to run the process until it gets stuck, because then there's some horizon, as you said, that I've gone into where I don't know what it's doing, and then I can't work with the output. I'm actually going to stop it, kind of just before this kind of event horizon at which I can no longer analyze it. And I'm going to work with that output, and just kind of miraculously, this is very often enough.
Thanks.
Okay, so here's just an instance of this random greedy thing. So it is a 15 by 15 board, and I'm placing queens on it uniformly at random. 8, 9, 10, 11, 14 queens. I want 50, but sadly at this point I'm stuck. There is an empty row and an empty column. I would want to put an extra queen in their intersection, but I can't because it's blocked off in both diagonals. Right? But here's what you can do to kind of fix this and turn it into a legitimate classical configuration. What I'm going to do is I'm actually going to take a queen off the board now. This one up here, I'm going to remove it. all right, well, this is just saying that I can't put a queen here in this corner. But now I've removed the queen in the, this second row from the top here. And I've made my situation worse, right? Because now I'm missing 2 queens instead of just 1 queen. But actually, my situation is in fact about to become better, because if I'm missing 2 queens, 2 empty rows, 2 empty columns, there are 2 ways that I could put them back on the board. I could either go with like the northeast and southwest corners, which in this case I know I can't because I already tried that and it didn't work. Or I could go with the northwest and southeast corners, which does work in this case, because it so happens that the diagonals running through those corners are all unoccupied. And the intuition for why this works, which I'm not gonna prove this now, but is that in a classical n queens configuration, you have n queens on the board, but if you count the number of diagonals that you have in each direction, you have approximately 2 times n, which means that if you have about n queens on the board, only half of the diagonals are occupied. So if you kind of like choose a diagonal at random, you have a 50% chance of hitting an empty diagonal. So what I need for this to work is I need the 4 diagonals that are going through these corners to be empty. So, it's not going to happen with probability really 50% to the power of 4. There are quite a few dependencies here that you need to take into account. But some statement like this does turn out to be true. There is a constant probability that if you just remove a queen from the board and then try to make this flip, that you'll win. And this turns out to be enough to complete like the output of the random greedy algorithm to a classical n queens configuration. Okay. Now, I'm done talking about the toroidal problem. Now I'm talking only about the, what my result actually is about, which is the classical queens problem. So if you remember, the entropy method for the torus, the crucial stage in the proof was saying that in the, I've drawn a queens configuration at random, I've ordered the n queens in it in a random order, and now I'm revealing them one at a time. And what I needed to know is what the expected number of available board positions is after t steps of this process. And it was this thing, n squared times what it says here. And the reason I was able to make this calculation is because of the symmetry of the torus. All n squared positions are exactly the same. They're all threatened by 4 queens in a complete configuration. But this is simply not the case for the classical problem, which is why you can't apply the entropy method directly. So in the classical problem, because of this issue with n queens, with only n queens, but 2 times n diagonals, not all the diagonals are occupied. So, over here on the left, what I've done is I've taken a typical, like a random 50 by 50 n queens configuration, and I've shaded each of the 2500 pixels according to how threatened it is. So each pixel, shares a queen with its row and column, but it can be threatened by either 2 queens, 1 in each diagonal, or just 1 of the 2 diagonals can be occupied, or maybe 0 of them. So the yellow positions here are completely threatened. They have 4 queens that are threatening them. The lighter brown positions and that are concentrated more in the corners are threatened by rows, columns, and 1 out of 2 diagonals. And then the darker brown positions are not threatened by diagonals at all. And so this is kind of like a typical pattern for a 50 by 50 configuration. On the right, I've done the same thing for a 1000 by 1000 configuration. So you can see that this kind of still persists. You still have a lot of places that are threatened by 4 queens, but also a lot that are threatened by only 2 queens. And because of this, it's difficult without some additional idea to make this estimate of the expected number of available positions. But what you can do is, say that I tell you, I promise you that in a particular n queens configuration, there are such and such positions that are threatened by 4 queens and such positions that are 3 threatened and such that are 2 threatened. And, so I have these variables D4, D3, D2, which tell you how many positions of each type are threatened. Then you could make a similar calculation and you could say, well, in this case, if I know that this is the case, then the expected number of available positions after t steps of the process would be, well, I could calculate it. It would be some formula depending on these di's. Now the problem is that we don't know a priori like what these di's should be. But what you can try to do is say, okay, well, d2, d3, d4 can't be just anything. I mean, for example, their sum must be n squared because you're covering all of the board positions. And maybe you can make some more sophisticated argument about how board positions interact and get better kind of understanding of this vector, d2, d3, d4. And if you can somehow maximize this expectation function over all of these vectors, then you would get an upper bound on the number of Queen's configurations. And in fact, this was done about 4 years ago. And so this theorem of Luria that says that Q of n, this is the one that I mentioned at the start, is at most, well, this thing, n to the power of e to the alpha to the power of n, where alpha is minus 1.58 approximately. And this is kind of the idea he used, but it turns out that this bound is still not tight. So you need an additional idea in order to kind of really think about, like, understand actual n Queen's configurations. So here it is. This is like going to be the final ingredient of that you need to understand these things. So what I'm going to do is I want to prove an upper bound on the number of n Queen's configurations. So I'm going to take my, just a square. This is at the moment not a chessboard. And I'm going to divide it into diamonds, the way that it's been done here. Why diamonds? These are just particularly convenient to work with for technical reasons. Now, I index these diamonds by I, and I have a probability measure. For every one of these diamonds, I have some number between 0 and 1, and their sum is 1. So I have a probability measure over these diamonds. And what I'm going to do now is, instead of trying to think of about all the possible n Queen's configurations, I'm going to say, well, right now, temporarily, I'm interested only in configurations with the following property. For every one of these diamonds, alpha, the number of queens in the diamond, or the fraction of queens in this diamond out of the total number of queens in the configuration, is gamma of alpha n. So what I do is, I have this square and I overlay it on the chessboard, and then I can count in each diamond how many queens are actually there. And I'm only interested in configurations with this property. The distribution of the queens on the board should match the probability measure that I have here on the square. And now this enables me to do an entropy method style proof. So once again, I'm going to say, let X be such a configuration drawn uniformly at random. So its bounding its entropy is the same as bounding the number of such configurations. So I'm going to say, let X1 to Xn be random ordering of the queens. And as before, what I want to do now is understand the conditional entropy in this process, where I reveal the queens one by one, x1, x2, x3, and 4. I want to understand the conditional entropy of xt, given that I know that the previous queens have already been revealed. So I have two things going for me. The first is that I know that this queen's configuration matches this distribution gamma that is known to me. So I can define an auxiliary variable, let yt be the diamond such that xt is in alpha. Where whatever queen is revealed at step t, it's going to be in one of these diamonds. So I just define this as a random variable. And then I can use another application of the chain rule for entropy and say that this entropy is actually equal to the entropy of xt given previous revelations and also yt plus the entropy of yt given previous revelations. Now, regarding kind of this guy over here, so what this is telling me is I've chosen a random Queen's configuration whose spatial distribution matches this gamma, and yt is telling me in which diamond basically a random queen from this distribution is located. So this entropy is basically going to be the same as just the entropy of the distribution gamma. Okay. So, bottom line is that I've translated this part of the entropy to just a function of gamma. And it turns out that I can do something very similar for this one. So, say that now I know that the next queen is going to be in this diamond over here. Now, because I know that the ultimate configuration that I'm constructing here or reconstructing here matches the spatial distribution gamma, it means I know how many queens are in each of these diamonds. So I know how many of these diagonals are occupied. I also know how many of these diagonals are occupied. Okay, and let's see if anybody calls me on this. I'm about to lie. But I know that every line here intersects every line here in exactly one position. And in a position where I see this intersection, I'm going to have a fourth threatened position. And in positions that are not kind of not contained in any of these lines, I'll have, 0 threatened positions. Sorry, not 0. They'll be threatened by the rows and columns, so 2 threatened. And of course, there will still be positions that are threatened in just one diagonal, but not the other ones. So this means that if I know that the spatial distribution of my Queen's configuration matches this gamma, and I know that the next queen is going to be revealed in this process where I'm revealing queens one by one is inside here, then I know inside here how many threatened queens there are of each type. And then I can apply this calculation that I had on the slides to use this entropy method. And this turns out to be tight. So this gives you some bound on the number of configurations, some upper bound on the number of configurations that match this gamma. What I then do in the proof is you say, okay, well, actually, I want to know if this bound is tight. In order to know if this bound is tight, I can imagine kind of a different process where I still reveal queens one at a time, x1, x2, and so forth. But now what I'm trying to do is construct a new configuration. So I skip the step where I draw x uniformly at random. Now I run a random greedy algorithm, similar to before with the toroidal problem, but with one key difference, where at each step, when I'm deciding where to put the next queen, I first draw a variable yt, one of these diamonds, according to the distribution gamma, and then I place the queen in a uniformly random available spot inside gamma. And you can use the same kind of switching completion argument to show that this does produce an n queens configuration that matches the distribution of gamma. And then you can kind of calculate the entropy of this construction process, and you find that it matches the entropy of the upper bound that I've kind of sketched how to calculate here. So this tells us that we've actually zoned in on the number of configurations that match this spatial distribution gamma. Okay. So this is like the workhorse of the proof. This tells you something a little bit more specific, but different also than in general, the number of n queens configurations. It tells you, well, if you want to know the number of n queens configurations that match a particular spatial distribution, so this is something you can find out. You can do this with entropy and with a random construction. And then kind of going back to the slides, you say, well, I don't actually care about Queen's configurations that match a particular distribution. I want to know about the total number of Queen's configurations. So you have to start doing some kind of abstract mathematical functional analytic arithmetic. You define what the particular class of spatial distributions are what I called gamma before, you have to define the ones that you actually care about. And then you define some entropy function on these, which is what you get out of this count, this entropy method count and this randomized construction count. And this entropy method kind of somehow governs the number of configurations. And then you get this theorem that, that if you fix your distribution gamma and you want to know how many n-Queens configurations kind of correspond to it, then this is really indeed governed by this entropy function. This space of distributions that I call quinons has a lot of very nice properties. It's convex. The entropy function is concave. Because of these, the entropy function has a unique maximizer. And also, as a metric space, in the way that I care about, these quinons are compact. And all of this boils down to the following thing. So now, if you want to know how many n-Queens configurations there are, what you need to do is find the distribution gamma that maximizes this entropy function. And there is exactly one distribution like this, and you can find it at least approximately using numerical techniques. And then you get this theorem that, well, whatever this maximizing guy, this distribution is, Q of n is going to be equal to n times e to the power of entropy function of maximizing thing, and all of this to the power of n. And then for the explicit bounds, what you need to do is kind of use numerical techniques to bound what this maximum value actually is. All right, and then you can ask, okay, well, what does this kind of optimizing distribution actually look like? And kind of, you get this very nice thing. So this is the density function of the distribution on the square that optimizes the entropy of n-Queens. And you can see that it's far from uniform. So what you can understand from here is that if you take a random n-Queens configuration, the queens are not going to be distributed uniformly at random on the board. They're kind of going to be concentrated on the sides more, not in the corners and not in the middle. Okay. All right, so that is pretty much it. This is just my backup in case the animation didn't work. I'll say that you do get this, using the numerical techniques, you do get this bound of, this 1.944 being like the governing constant. This was actually predicted about 10 years, a little more than 10 years ago in a physics paper, but there was no proof here. This was using just numerical simulations, but they got a remarkably accurate estimate, which has now been proved. All right, and that's it. Thank you very much.
Hi.
Hi.
Yeah, hi. Yeah, great talk. Let me ask about kind of other problems which might or might not be related and solvable by these methods. So one would be like counting tilings. So if you have a shape of a tile that has to sit on a lattice, so there is a similar kind of an exclusion principle. Do you think you could study those?
I mean, I think certainly, I think certainly, yes, there could be some things, similar techniques could work for some of those problems. Let me put it that way.
Okay. And I guess another general class would be where there's some randomness, there's some ensemble of problems, like, you could take the 8 queens where you allow some random jags in the lines, but of course there are many classes of problems you could study. So you generate the original hypergraph, through a random process, and then you have this type of analysis.
Yeah, I mean, I think this is, it is, obviously it would depend on the specifics, but I think it is very likely that for that sort of problem involving randomness, these sorts of techniques could play.
Yeah, also because a lot of these combinatorial optimization, random, of random instances, can probably be, fit in that mold. I think like the random stat problem, but there's lots of them. Okay.
Yeah, I mean, actually, somebody like so Peter Kivash, who I've already mentioned in this talk, he came up with the toroidal solution, but also in a certain sense is like kind of the godfather of all these methods.
Yeah.
Like mentioned to me that he did see similarities between this and random k-sat.
Yeah.
Yeah. Yeah. I think, you know, I hope that I or others will be able to find other very nice applications. I think there should be some.
Yeah. Oh, let me just throw out another generalization, which sounds much harder to me, but maybe suppose you were allowed to have up to 2 queens on each row, column, or diagonal.
Well, okay, so I mean, this is the sort of thing that is either very hard or very easy, I think.
Okay.
So the way in which it could be very easy is that it's possible that the best thing you could do is just to take 2 of these, you know, n queens configurations with just 1 queen and like overlay them. And then you would have, I mean, you have to do something about making sure that you don't have 2 queens sitting on exactly the same spot. That's probably not hard to think about, but then you would have a configuration satisfying your constraints. So the question would be, is this the best you can do? Which, you know, I don't want to say anything now. I don't have any intelligent guess. But yeah, I mean, definitely these sorts of questions are, and it sounds interesting.
Yeah, I agree. I think Professor Douglas' comment is remarkable. I'll be very curious about like a generalization of n queen. And I have a related question also on generalization. What's your insight on this problem for knights? Like I've been always curious why like n queen is so popular and not so much appearance on the knight problem, for example.
Well, so they have kind of different characteristics. And in particular, like the way that knights move, their threats are much more local. Like they only threaten a small area of the board.
Yeah.
Whereas queens have like more global and far-reaching ability to kind of threaten things, right? I mean, the way queens threatens, their size of their threat range grows together with the board. And this is like kind of a crucial property for these sorts of methods to be applicable. When you're looking at the more local things, you usually use more kind of fine-tuned, ingenious construction sorts of things, rather than like kind of these coarse, random things. That's why the problems probably don't usually come up together.
I see. Do we have any other questions?
Yeah, I have a small question. What's the structure of the space of solution that you can say? I mean, obviously there is like a 4-fold symmetry that you can just rotate the board, but except for that,
Well,
is there any
in fact,
known
I would say an
structure?
8-fold symmetry. Well,
Sorry?
so I think there is an 8-fold symmetry in the sense that, you know, you have the dihedral group acting. Okay, I don't have a good slide here, but you have the dihedral group acting on it. You can rotate it and you can reflect it. This is for the classical problem. For the toroidal problem, you have a much bigger group because you can also cycle the board.
Yes, but is there? Yeah, that's what I meant. But is there any other known structure that can be conceived?
So, not in the sense of symmetries. Like it's very likely that I mean, you'd have to think what the best way to formalize this is, but that there are no additional like symmetries. What I can say, one of like kind of the corollaries of the methods that I used is this theorem, which I kind of skipped through, but it says that so you have this optimizing distribution of queens. So it turns out that if you just take a random distribution, a random n queens configuration, and ask how are the queens distributed spatially, so it'll look like this, right? So it won't be a uniform distribution. It won't be like anything else. It'll be very close to this fellow over here. So in that sense, we understand like the structure of this a little bit, but kind of in other senses, I think like we really have very little understanding, which is maybe part of the reason why there wasn't much progress on this problem until like these modern methods were known.
Let me ask maybe a structural question that you might know the answer to. So you talked about in the like modifying a configuration to produce a solution. So if you imagine there are two queens and they map out two rows and two columns, and now you do the exchange where you have the 4 intersection points and you take the 2 queens and you put them on the other 2 intersection points and you call that a move. So the whole set of configurations, there's this graph where edges are moved, and is it connected?
I mean, that's a great question. I've thought about it. I do not know the answer, despite your, that would be, I mean, that would be very interesting, because if it is connected, I would say then there is a good chance that just performing the switches would give you a rapidly mixing Markov chain in the space, and that would be also very nice to have.
Yeah.
But I don't know. I think that my methods are too coarse to actually prove this. But
and there's no physics. The physicists didn't study this. I mean, how did they generate their configurations?
Well, so you can do other things. You can allow yourself to just remove, say up to 20 queens from the board.
Yeah, okay, that's right. Certainly there are moves for which this will
Right.
eventually.
And that's what they, so in the paper I mentioned, that's what they did.
I see. Okay.
I have a follow-up question. So earlier you said the 9th question is more local. Would that make the problem in general harder or easier? What's your kind of guess?
It makes it different. So I don't want to talk about the Knight's question specifically, because I actually don't know kind of what the state of the art there is. But I happen to know that for like the equivalent King's question, the answer is known to a very high degree of accuracy. Like there is like it's a terrible formula, but it is very explicit about the number, like far more accurate than like what I have for the Queen's problem. So I think in like those sorts of problems, like there's always some chance that you can get something. I mean, maybe in these problems too, that there's some chance that you can get something, but we don't know how to do that yet. For the more local things, that you can sometimes get very accurate things.
I see.
Yeah.
That's very helpful. Thank you. Okay. So is there any other questions? Before we close this, I just want to make a remark that if you're interested in reviewing this talk further, please reach out to Dr. Simkin directly to request a recording. Michael, if you want, you can put your email there, but I think your email is also CC'd in the notification and announcement, or you can also email me. I'll forward the request to Michael. Thank you very much for everyone coming to today's seminar, and I think it's really a great start. I look forward to see everyone again next week and in the coming weeks at the same time.
Thank you very much.
Thanks.